In this video, we're going to be solving applications involving variation. Now consider the variation models y equals kx. That would represent a direct variation. And the model y equals k divided by x, which represents inverse variation, or inversely variating. Or y equals kwx, which would represent joint variation. So in all of these situations, if we know the values for x and y, or in joint variation, x, w, and y, we can solve for k. And then once k is known, we can write a variation model and use it to find y as long as x is known. Or for joint variation, find y as long as x and w are known. And this concept is the basis for solving many applications involving variation. And there are 4 steps. First, you want to start by writing a general variation model that relates the variables given in the problem, letting k be the constant of variation. Then, you want to solve for k by substituting known values of the variables into the model from step 1. Then, you want to substitute the value of k that you found into the original variation model from step 1. And then, you want to use the variation model from step 3 to solve the application. Let's put this procedure into practice. In the example we have here, it says the amount of an allergy medicine that a physician prescribes for a child varies directly as the weight of the child. Now remember, the directly is multiplication, right? Now clinical research suggests that 13.5 milligrams of the drug should be given for a 30-pound child. So let's begin by setting up our model. So we'll begin by defining a couple values. We're going to let A equal the amount of medicine, and we're going to let W equal the child's weight. So if we're setting up our model, we're going to have A equal to K times W. And so that's really our step 1. We've set up our model. And now we're ready to look at what would step 2 look like. Well, we're going to fill in the things that we know. Now we know that clinical research suggests that 13.5 milligrams of the drug. So that's going to be the amount of medicine. That's going to be our A value. And it says a child weighing 30 pounds. So our 30-pound child is going to be our weight. So we can plug those values in. So we can now put 13.5 equals K times 30, and then again there's our amount of our drug and our weight, and we are now ready to solve for k. So we can do this by dividing both sides by 30, and that's going to tell us that k equals 0.45. So that's going to be our constant of variation. So now we can set up our equation, which is our step 3, and we get that A is going to equal 0.45 times W. And now we can use this equation for different weights. For example, how much would be prescribed for a 50-pound child? Well, we just need to plug in the number 50 now to our equation. So A equals 0.45 times 50. And when we plug that in, we're going to find that the amount of medicine should be 22.5 milligrams. So how much should be prescribed for a 60-pound child? Well, this time, instead of plugging in a 50, we're going to plug in a 60. And this is going to tell us that we should have 27 milligrams for a 60-pound child. And we can even change it up. In problem C, it says a nurse wants to double check that the dosage on the doctor's order of 18 milligrams. So for a child of what weight is this dosage going to be appropriate? So remember, the amount of the drug is our A value. So now what we're looking at is the 18 equals 0.45, and now we're looking for the weight. So I can divide both sides by 0.45 and get that W equals 40 pounds. Now notice that the more medicine is given in proportion to a patient's weight. So a 60-pound patient weighs twice as much as a 30-pound patient, and the amount of medicine given is also twice as much. And this is the consistency with the direct variation.